Welcome back. We are doing the Nature of Light Worksheet Consolidation Part 2, Worksheet 2. And we have just done questions 1 and 2 in a previous video. We're now going to go 3 onward. So question 3 is about an annihilation. So we have a proton and an antiproton meet, and they annihilate each other. And as we know from our studies of the Big Bang Theory, annihilation happens when a antiparticle and a particle meet itself, converting both particles back into their entire energy equivalent. So we're going to work out how much energy would release with these two particles meeting. So question 3, let's turn that up. So question 3, so here is our proton. That's our proton and our antiproton. Okay, so we normally put a line above it to say it's the anti. So if a proton was P, that would be P. This would be anti-P. Okay. Now they are coming together and they're going to annihilate each other into pure energy. Okay, at the energy equivalency. The thing we need to remember about the antiparticles is that they have opposite charge characteristics, but they have the same mass characteristics. So the mass of this proton is 1.673 by 10 to the minus 27 kilograms, and same with this one over here. So the amount of mass that is going to be converted into pure energy is going to be 2 lots of this value here. So what is the energy equivalent? The energy equivalent is given by mc squared, and we now know that that should be m0 c squared. This is the rest mass of these, and we are going to assume that these two protons are meeting at very low speeds. Okay, we're not going to take into account their kinetic energy. We're just going to simply make these two meet. Okay. If they were traveling relativistically, we might have to take into account that there is some kinetic energy involved in this, and we would have a larger mass recorded. Okay, so what we are going to do is take the 2 times the mass of each of those. So it's 2 times 1.673 by 10 to the minus 27, and then multiply that by c squared to find the energy equivalent released. So it is 2 lots of 1.673 exponent negative 27 times by 3 exponent 8 all squared, and it comes to 3.01 by 10 to the minus 10 joules. Okay, also known as 301 picojoules. Okay, right. Okay, so let's move on to question 4 now. Question 4 says a space station has a proper length of 6 kilometers in diameter. An observer on the space station measures a spacecraft. Okay, so a space station and a spacecraft. So let's not get them confused. And the spacecraft is traveling at 3/4 of the speed of light. And the observer measures the spacecraft to have a length of 115 meters in length. Okay, so we're asked to find the proper length of the spacecraft and the length of the space station as observed by the pilot of the craft. Okay, so let's work this out. As always, the first thing we're going to do is look at our velocities and determine the gamma factor for this situation. So question 4, the gamma at 0.75 c would equal, let's straighten that up a bit. That's better. Would equal 1 over the square root of 1 minus 0.75 squared. Popping that into our calculator. It's 1.511. 1.51185. I'll just go there. Make that 86. Okay. Rightio. So we're talking about length here. So we are thinking about length contraction. So LV equals L naught on gamma. So most of our formulas have the gamma up the top. Just remember, for this formula here, the gamma is in the denominator over here. Okay. So what are the, let's have a look at a situation. Let's just draw a little diagram. So here is our space station. Okay, and here is our craft. Okay. And the craft is moving at 0.75 C forward. As a pilot on this craft, you would see the space station go that way at 0.75 C, okay, and you would be not moving at all. So remember, it's depending on whose frame of reference you're talking about. So we're going to talk about the what is the proper length of this space station here, spacecraft, because the space station observes this here to be 115 meters. This would be the observation of the contracted value. The pilot should see a larger value there. Okay, so the space station is going to be considered to be stationary, and therefore, as a result, they will see a shorter length because of length contraction than its proper length. Okay, so this 115 is the length at velocity. So it's 115 equals L naught times gamma, which is 1.51186. So the length at length proper would be that value, which is gamma, times 115, which is 178.86 meters, or 178.9 meters. Okay, that was A. Looking at B now. What will be the length of the space station as observed by the pilot of the spacecraft? So remember, it depends on who's stationary, depends on what frame of reference. A few moments ago, we had the space station pretending it's stationary and the craft moving, but from the pilot's perspective, they are stationary and it is the actual space station that's going to be moving backward. Okay. Now we know that the space station has a proper length of 6 kilometers in diameter. Okay. We're going into a circular one. And therefore it's going to have, firstly, the gamma factor is the same for both of these situations because it applies equally. So this is the proper length, and the pilot would see this 6 kilometers being contracted to a smaller value. So LV would equal L naught on gamma. So we know that this is 6 kilometers to begin with, and it is now divided by the gamma factor, that there. So let's just work that one out. So we've got 6 divided by 51186, and therefore it's going to be 3.968 kilometers. Let's just round that. That becomes 399. So that becomes 4 kilometers if we start to round it up. Okay, so the pilot observes this here to be 4 kilometers. Right, going to question C now. The space station is now, we're giving a bit more information. The spacecraft, I should say, has a rest mass of 3,500 kilograms. We're going to now work out the measured mass of the craft as it moves past the space station. Remember, because it's traveling this, we will observe it to have a larger mass. Okay, we observe that mass to be larger. We're going to calculate the momentum of the spacecraft and also the kinetic energy. Okay, so let's go through. Now, we've just calculated as for A, that the gamma factor for this situation is 1.51186. So we'll just use that value all the way through. We don't need to calculate again. So the measured mass, we're going to use this formula here, which says the mass which is measured at a relativistic speed is going to be larger than the rest mass by a factor of the gamma. So it's just going to be the rest mass multiplied by gamma. So it's 1.51186 times 3500. So it's 1.51186 times 3500. And it's 5,291.51 kilograms. Okay, or we'll just round that to 5,291.5 kilograms. Okay, a very simple calculation there. The second one was, what was the momentum? The momentum at velocity is gamma mv. The gamma is 1.51186 times the mass of the craft. Now that's the m naught, that's the original mass, that's the rest mass, because remember, in reality, all this formula is the Newtonian formula, which is mv, but this m has now grown to be that, to gamma m. Okay, so that's all this formula here is. So that number there is the rest mass, which is 3,500, times its velocity. Now it's traveling at 0.75 speed of light. Don't forget to also multiply by the speed of light, which is 3 by 10 to the 8th, not just by that one. So it is 1.51186 times the 3500 times 0.75 times 3 exponent 8. And we get that the momentum is 1.19 by 10 to the 12. Also, we could round that to 1.2 by 10 to the 12 Newton seconds. Okay. C, sorry, that wasn't B, that was D, sorry. This would be E. E, we're asked to find the kinetic energy. So the kinetic energy, there are two formulas you could use. It's gamma m naught c squared, which is the mass of, that's the energy equivalency of the mass at motion minus its rest mass energy, which is this one. You could use that, or you could use the factored form, which is so much easier, which is m naught c squared gamma minus 1. Okay, so the difference between this and that value would have to be the kinetic energy, because remember, this value here is simply measuring the extra energy in the situation, which is kinetic in this case. Rightio, so putting the values in, we've got 3,500 times c squared. I'll just put the c squared. Gamma minus 1. Now the gamma is 1.511, so it's going to be 0.51186. So I'll just move that that finger away there. Okay, so it is going to be 3,500 times 3 exponent 8 squared times the gamma factor, which is, well, it's gamma minus 1, 0.51186. And it is going to be 1.612, I'll just go there, by 10 to the 20, and it's joules with kinetic energy. Okay, rightio. So that's questions 3 and 4.